Welcome to lecture number 4 on antenna theory and design. My name is Professor Levevia. The presentation outline will cover a number of things today. Number one, we'll look at basic antenna parameters. That is after we've done the definition of what antennas are and what antennas are not. Then we'll look at types of antennas, antenna radiation mechanism, antenna design, and where we can apply these antennas in our communication systems. So let's begin with a word of introduction. What is an antenna? An antenna is nothing but a device, an electronic communication component device that converts electrical signals into electromagnetic waves. That is, if you talk of it in terms of from the transmitter side. So from the transmitter side, it will convert electrical signals into electromagnetic waves. But from the receiver side, it will actually convert these electromagnetic waves into electrical signals. Now, an antenna plays a number of functions in most of these communication systems. Some of the essential roles of an antenna includes its use in radio and TV broadcasting, mobile communication systems, satellite communication systems, radar systems, Wi-Fi as well as WiMAX. So any wireless communication system needs an antenna, and that's why we are discussing this topic today. So let's look at some of the basic antenna parameters. There are several parameters that are very, very important to understand, even before we look at the types of antennas. Number one is what is known as radiation pattern. Now, by definition, a radiation pattern is nothing but a graphical representation of how an antenna radiates energy in space as a function of direction. So we're just graphically, for example, if you look at this diagram, it shows that this antenna is actually radiating in this direction, right? In the direction, right? But there are these other small radiations, including the back radiation, which is known as the back lobe. The small side radiation are called side lobes. And then you've got the main direction, the main representation of where this antenna is intending to radiate some energy. So the direction is in the 90 degrees direction. And this one is called the main lobe. So you have the main lobe here. Then you've got these small lobes called side lobes. And then you've got the back. So it's like behind an antenna. Some energy may still go behind, and yet the intended direction is in this direction, but you've got others going in that direction, others going these, which we call the side lobes, and then you've got small radiation, small energy being radiated in the opposite of the intended direction, which is this main direction here, right? So when we talk of radiation patterns being omnidirection, it simply means that you are radiating in all angles, in everywhere. This is common, especially when you are doing the radio and the TV broadcasting. You want to send a signal everywhere, across 360 degrees. But it may also happen that you want to send, a signal in a specific direction, maybe in the southern direction or northern direction, at 30 degrees angle from where you are, or 60 degrees angle from where you are, 90 degrees angle, and so on. Then that becomes directional, right? So it means you are radiating these patterns you're radiating these signals in a directional format. Omni means 360 degrees, directional at a selected angle. Okay, so let's look at further, let's look at another parameter of interest. But maybe before we go there, you may be interested to know, yes, you'll be interested to know that as we talk about these radiation patterns, you can actually measure how concentrated an antenna's radiation pattern is in a certain direction. And that measurement is usually taken with a reference antenna, which we call an isotropic antenna or radiator. So when you measure the concentration of certain of an antenna's radiation pattern in a certain direction in comparison with a reference, right? An ideal transformer. I mean, an ideal antenna, then that is what is called directivity. So directivity is a measure of how concentrated antenna's radiation is in a certain direction compared to an ideal antenna. And the general formula for calculating directivity is 4 pi U max divided by radiation power. So where U max here simply means the maximum radiation intensity. So if I know the radiation in my intensity divided by the total radiated power, which will be in watts, and then I can actually calculate it using this general equation. But you can also calculate the directivity given the gain, G. So if I know the gain, G, and I know the efficiency, which is denoted by this symbol here for efficiency, basically that is your efficiency there. So if I divide that into gain, I still get the directivity. So it means that the more efficiency tends towards 1, when it is approximately 1, then you have gain, you have actually directivity almost being equal to the value of the gain. Okay, so let's move on to another parameter. So we've looked at the radiation pattern. Now we've looked at the second one, which is directivity. Related to directivity, remember we have talked about gain. So let's talk more about gain. What is gain by definition? So gain, antenna gain, is a measure of how effective an antenna converts power into radio waves. Remember, you have an electrical signal. If it is from the transmitter side, that electrical signal has to be converted into an electromagnetic wave or a radio wave. So the measure of how effective that antenna can convert all of that electrical energy into an electromagnetic waves or a radio wave in a certain direction compared again with an isotropic antenna or a reference antenna is basically what is defined as gain. So the letter for gain is G, and given directivity, you can actually multiply by efficiency. Basically, you get the value of gain. So you just need to know the directivity. I know the efficiency, then I can also calculate the gain. But further to that, you can actually calculate what is known as, you can actually convert that gain into what is known as a linear scale. Remember, gain is measured in dB, decibels. So you can actually convert that into a linear scale by simply taking an ant log of whatever you are given in decibel. So when I do the ant log of that, I get the gain or I convert it to a linear scale. So this is nothing, the equation you are seeing here can actually be done using a calculator. It's essentially the same as an ant log. Okay, antilog of G gain in decibels. So just take the antilog of that. We are going to essentially convert gain from decibels to a linear scale. Okay, so let's move on now and look at the next parameter. The next parameter has to do with which is the fourth parameter really, is known as effective aperture. By definition, an effective aperture of an antenna is a measure of how much an antenna can capture signals from an incoming electromagnetic wave. This is mainly measured at the receiver end. So if you have an incoming electromagnetic wave, the measure of how much that antenna can capture most of those electromagnetic waves, that measure in meter squared is known as the effective aperture. And it's actually calculated from the equation antenna aperture equals gain. So again, it's a function of gain, and then it's also a function of wavelength. So you square the wavelength multiplied by gain divided by 4 pi. That's how you calculate the antenna aperture. So you just need to find the value of gain, and you just need to also know the value of antenna wavelength, which is usually measured in meters. So let's do a simple example here under effective aperture. Suppose you have a receiving antenna that has a gain of 10 dB. dBi there simply means that you are measuring that with respect to an isotropic. So the I in the dB, the I after dB simply means that gain is with respect to a reference antenna, which is essentially an isotropic antenna. So at 3 gigahertz, find its effective aperture. So the first step in trying to solve this is to convert gain, right? So you convert gain into a linear scale, take an analog of that 10 dBi, you get 10. Step number 2, find the wavelength, which is basically calculated from the speed of light divided by the frequency, and the frequency in this case is 3 gigahertz, that is 3 times 10 to the power 9. And then you have the speed of light, which is 3 times 10 to the power 8. When you divide that, you get 0.1 meters as your wavelength. So this then means that once you get your 0.1 as your wavelength, then you can calculate the aperture of an antenna. You know the wavelength is 0.1, the gain is 10, and then you substitute your 10, you substitute your 0.1, square it divided by 4 pi, and then you simplify that, you're going to get an antenna aperture of essentially 0.08 meters squared. So take note of the unit for antenna aperture. This is essentially measured in meter squared. Okay, so with that example now, we can look at the next parameter. The next parameter, which is parameter number 5, is essentially known as the freeze transmission equation. So I thought I should bring this parameter because it's also very important in antennas. Once you know the received power, you know the transmitted power, you know the gain at the transmitter, GT, you know also the gain at the receiver. You can actually calculate the received power. Once I know transmitted power, gain at the transmitter, gain at the receiver. I also know the distance between the transmitter and the receiver R, okay? And then I also know the wavelength. I can calculate the received power using the freeze transmission equation, which is given by this big formula. So take note that GT and GR is transmit and receive antenna gains. And also take note, R is the distance between antennas. So when you substitute there, you can actually calculate the received, the received power from this freeze transmission equation. Let's do an example here just to illustrate the point. Suppose you are given, two antennas that are separated by 100 meters. So your array there is 100 meters. And you're also given that the transmit power is 10 watts. And you know that the gain for the transmitter and the gain for the receiver each given as 2. Then you can actually find the received power given the frequency. If the operating frequency is 1 gigahertz. So again, using the Friis equation, transmission equation, this one, you can actually substitute, but before step number 1, first of all, calculate the wavelength. Wavelength is speed of light divided by frequency. And since here we have 1 gigahertz, so it's basically 10 to the power 9 into 3 times 10 to the power 8, you get a wavelength of 0.3 meters. Then you go to step number 2, substitute all these parameters that are given. You know the transmit power is 10 watts, the gain at the transmitter and the receiver are each 2. And then you have your wavelength 0.3, which you've just calculated. Square this, divide by, of course, 4 pi, your distance between the transmitter and the receiver is 100. So when you simplify this, you get your received power as 2.28 times 10 to the power minus 6 watt. So take note again how to calculate, depending on which parameter is given and missing, you can actually calculate the missing parameters. Next, I want us to talk about another antenna parameter. These are basic antenna parameters. Parameter number 6 is known as the bandwidth. We all know that antenna bandwidth is the range of frequencies over which an antenna operates effectively. And mathematically, it's the difference between the highest frequency and the lowest frequency. Or you can express it as a percentage where you have the highest frequency minus the lowest frequency divided by the center frequency times 100. So essentially, that's how you calculate your bandwidth percentage. And the bandwidth is, you just need to know the highest frequency and the lowest frequency, the difference between the two. So this parameter is important, like I said, because it determines, it specifies the performance of an antenna, and you need to know how to calculate it as well. Okay, the next parameter is known as polarization. What is meant by antenna polarization? Now, polarization can either be linear, circular, or elliptical, and by definition is nothing but direction of rotation of electric field around the antenna. Orientation of it has to do with electric field, really. What is the direction? What is the orientation of the electric field or direction of rotation of the electric field around the antenna? If it is linear is in if it is linear has two parts, either linear rotating in the vertical direction as shown in this diagram here. So you can see this is your antenna here. That's your antenna. And then you've got the direction of the signal, radio waves in this direction, right? But then you have, you have, the magnetic field is rotating at 90 degrees with the electric field. And so that's your magnetic field, but the electric field is actually going in the vertical direction. As you can see, this is actually the direction of electric field in the vertical direction, basically going up and down in that direction. Then it can also happen that, again, you have the electric field going in this direction, which is the horizontal, while the magnetic field goes in the vertical direction. But remember here, when we talk of polarization, we are interested in the electric field. Where is the direction of the electric field? So if it is moving in the vertical direction, then it can either be in the vertical or horizontal in constituting what is known as linear polarization. There's also secular polarization, where now instead of going vertical or horizontal, it's going in a secular direction, or even in an elliptical direction. All those are basically methods of uh, electric field direction, or basically known as polarization. Okay, the next parameter we are interested is parameter number 8, known as the impedance matching. This one we earlier met it when we were doing transmission line. Impedance matching is the process of making the antenna impedance equal to a transmission line impedance. And we all know why impedance matching is important. So right before the antenna, you have on the other side the transmission line coming from the last amplifier stage of a transmitter to the antenna. Okay, so that line will have the characteristic impedance. And then by the time you're putting that antenna has got resistance, has got impedance, what we call antenna impedance. So that antenna impedance must be equal to the transmission line impedance to avoid reflections. We all know the side effect. If the two are not matched, then you're going to get some of the energy from the antenna going back to the transmitter. And you don't want that. You want all the energy as it is coming from the transmitter to be radiated, to be converted into an electromagnetic waves, and then be broadcasted in a certain direction. So impedance matching becomes very, very important to minimize signal reflection. So for typical transmission lines, you always find that for RF systems, you have a characteristic impedance of 50 ohm, 75 ohm for TV systems. So it means that if the transmission line impedance is 50 ohm, then the antenna impedance must match that. It must actually be equal, because that becomes now the load resistance. So the antenna impedance is essentially the load impedance, so it must be equal to the characteristic impedance of the transmission line. So again, this was covered in the topic transmission line, but it also becomes very, very important under antennas. The next parameter, which is parameter number 9, is beam width. Beam width is the angular width of the main radiation lobe. Remember, when we were talking about radiation patterns, we talked of the main lobe, side lobes, and the back lobes. So beam width is the angular width of the main radiation lobe. So the width of that main radiation lobe of the antenna measured between points where the power drops at specific or specified levels. And you can calculate that if you know the diameter of that lobe, okay, divide that into the wavelength multiplied by 70. So it's 70 times the wavelength divided by the diameter. And let's do an example for you to, maybe before we do that, just to show here, you actually know that in this diagram, it illustrates what we're talking about. You have the back lobes, which is right in radiating that direction. Then you have this one, which is basically the main lobe, which shows the main direction of where you're radiating. And then you have also the side lobes. These are the side lobes. All these are side lobes. So there are two types of beam width. There's what is known as half power beam width, HPBW. Now in half power beam width, this is the most commonly used one. It is essentially the angle between points where power is half decibel. So in short, it is actually the angle. It is this angle here, right? That angle between right? This, you can measure it between the max, the negative decibel points of the main lobes. So it is essentially this angle that you are measuring there. That becomes the half power beam width. Then you can also measure from the side lobes, right? From these side lobes, the minimum part there, that angle there, okay, between the side lobes and the main lobe. Okay, so angle between the first nulls or zero radiation points on either side of the main lobe. So that angle there becomes essentially the first null beam width. So let's do an example to illustrate how you can calculate this. Remember, we have given the formula for beam width as theta equals 70 multiplied by the wavelength divided by the diameters of these lobes. So depending on which diameter you are given, if you are given between the first now, right, it means they're asking you are given that angle between the 0 points, the zero radiation points, and the main side lobe. Okay. Or you can measure it within the main lobe, which is basically half power beam width, which is type number 1. Let's see if I have an example here to illustrate this. Okay, suppose you are given the beam width. Okay, you are given to estimate the beam width of a parabolic antenna with a diameter of, okay, so you are given the diameter there, and the frequency is also given, which is 10 gigahertz. You can calculate the beam width using 70 pi, 70 multiplied by the wavelength divided by the diameter there. So first of all, let's calculate the wavelength in step number 1. You know, wavelength is speed of light divided by frequency. You get 0.03 meters. That's your wavelength, therefore. And then the diameter here was given in terms of as 1 meter. So it will be 70 times 0.03 divided by 1, since everything is in meter. And you're going to get that angle, which is essentially 2.1 degrees. Okay, so let's move on now and look at types of antennas. Types of antennas. There are several types of antennas, but we'll start with one of the basic antennas that we have, known as a dipole antenna. The dipole antenna, what is key to take note is that essentially it has two wires, right? It has two wires, as you can see here. There is this part, the wire bent like that, and another wire bent like that, and then you connect here your cable, you connect here the cable. You basically be able to use this to radiate or even receive electromagnetic waves. Yeah, so that is called a dipole. What is important to take note in the design of a dipole, the distance between this wire and that wire must be at half wavelength. Okay, that distance, which is this distance here, must be at half wavelength. So if I know the wavelength, we all know how to calculate wavelength. So depending on it's the speed of light divided by frequency. So depending on what frequency you're operating, you can actually calculate the wavelength. And once you know the wavelength, then you measure from this center here, going in that direction, right? And also from here up to there, that distance must be quarter wavelength. On my left here, what I've done is to show the similar dipole but the actual one, you actually see that, the actual one will look as follows. You see the first wire there and the second wire there, and they have this being mounted now to the actual cable. This is the connecting part, and where it goes here could be your TV or whichever receiver or transmitting device that you have. So that's basically a dipole antenna. And as we look at dipole antennas, I want us to look at the next part within the dipole antenna, essentially a small calculation of how you can design a half-wave dipole antenna operating at 900 megahertz. So the first thing we need to know is to find the length. Okay. So the length is essentially, we said in the design, first of all, you need the wavelength. The wavelength, which is given by C divided by F. And once you find that wavelength, its length is nothing but half wavelength divided by 2. Okay, so it is essentially what I've done here is, in place, we know that if half wavelength is this, we can substitute it in this equation. You get C divided by F divided by 2, which then gives us C over F times 1 over 2. Change the division into multiplication. And when you multiply that, you get C divided by 2F. So essentially here, I was just trying to show how the L here has been derived in that equation. So given these parameters, once I know my wavelength, which can be gotten knowing these two parameters, then divide that by 2, and then you get the length of a half dipole as essentially this. Take note here, your frequency is 900 megahertz, which is the same as 900 times 10 to the power 6 hertz. So you can, in your design here, you're interested in knowing the length of that dipole. So the length is really determined by the frequency, and that frequency also is what informs the wavelength. So you need to take note of that in the design of dipoles. Dipoles, anyone can actually design this. These are very, very common and designed by even people who have not advanced in school. They can easily make a dipole and connect it to their television or radio systems. The next type of antenna, or before we go there, is I want us to talk about radiation resistance in relationship to a dipole antenna. Radiation resistance is the equivalent resistance of an antenna that represents the power radiated as electromagnetic waves. And the concept behind radiation resistance is that it's really not a physical resistor, but it models how effective an antenna converts input power into radiation, right? So that equivalent resistance of an antenna, that represents the power radiated. So part of the antenna's total input impedance. So remember, we had talked of Z and the impedance. When we talk of impedance matching, we talk of, so it forms, that radiation resistance, it forms a part of that antenna impedance. Next thing to take note here is, how do you calculate this radiation resistance? There are two formulas that we can adopt here. If we know radiated power and we know the current flowing into the antenna. Square that, you get your radiation resistance. So you need to know radiated power. You also need to know the current. So when you square that, you get essentially. So from this equation, again, you can actually know how to calculate the radiated power. You just need to know the current and also the radiation resistance, which is measured in ohms. The second way you can actually calculate radiation resistance for dipoles is if you know the wavelength, right? And again, if that wavelength is far greater than the length of a dipole, this is basically where the dipole is very short, and that means your wavelength is very large. You can calculate it by 80 pi squared multiplied by L divided pi divided by wavelength. So again, there you need to know the value of your wavelength. But for half dipole, the standard is just the wavelength divided by 2, and in most of these, it's actually 73 ohm as a value of radiation resistance. It approximates that. Okay, so here there was a question where you're supposed to find the radiation resistance for half dipole. Since it's half dipole, it's a wavelength over 2, and it approximates essentially 73 ohm. But yeah. So next, let's move on to the next type of antenna, which is a monopole antenna. A monopole antenna is nothing but half dipole plus it's similar to a half dipole, but it has a ground. It has also a ground plane. It's very, very popular, especially in mobile communication. So it's basically an improvement of a dipole antenna, and I will not talk much about it. The next type is known as a Yagi-Wood antenna. This is very common. These were very common old type of antennas that were used for TV reception. Those old televisions were using mainly Yagi-Wood antennas with a number of what are known as elements, antenna elements. So this one is used to radiate as well as to receive the signals, mainly for used as for TV reception antenna, and this direction. So you have to mount it in such a way that it faces a certain direction where it can capture a lot of signals. Then you've got the parabolic reflectors. These are common. They are the ones used for DSTV, for satellite communication. They are essentially dishes that aggregates, electromagnetic waves and then route it through a low noise block or through a low noise amplifier. So they are highly directional and they have a high gain, and they are mainly used in satellite communication. Then you've got a patch antenna. A patch antenna, this is what is common in most mobile communication, most Wi-Fi systems, GPS, mobile phones. They are very short. You can't easily see them, but they are there. They operate at very, very high frequency. It's compact and low profile. But if you look at the inside, really there, you have the front. If you look at the front view, it has got what is known as a strip line, or essentially a patch, and then that patch is covered through some material known as a substrate, and then that substrate separates between the patch antenna and the ground, right? So the ground and the patch antenna must be separated. The ground will act as a negative, while the patch itself is the one that will act as the positive in terms of capturing the signal. And then you've got a mounting connector there, SMA connector, that is used basically to connect this. So like I said, these are very, very short antennas, very advanced, intended to operate at high frequency in the gigahertz, such as what we see in mobile phones as well as Wi-Fi systems. So the list of types of antennas goes on. There was also what is known as horn antennas and so on and so forth. So we can actually keep on, but these are the basic antenna types that you need to be aware of. Of course, these are the ones that are used in most of the modern communication as well. So let's look at radiation mechanism. How does an antenna really radiate energy? So you have from a transmitter through the transmission line, current flows in a conductor. So there should be some current flowing into the conductor. And the principle there is as this current is flowing through the conductor towards the antenna, then the charges, like the electric charges, that will begin to accelerate. And as they are accelerating, these accelerating charges will produce what is known as electromagnetic waves. Basically, they will be transduced. So from into an electrical energy into an electromagnetic waves. So radiation will be strongest where current varies. So you need this current to be oscillating, positive and negative. If it is DC, then the radiation will be very, very low. That's why we are saying here, the key insight, where you have uniform current, meaning current is like a DC, radiation will actually be zero. But the moment you have some oscillations at a given frequency, that's why that electrical signal must be oscillating at a very, very high frequency for you to have radiation which is strongest, right? So it must be time varying current, which means it must be oscillating. Then you have radiation. So the key thing I want you to take note here is if you are injecting DC towards your antenna, you get zero radiation. You need an alternating voltage and currents coming from your transmitter, or if it is coming from, remember, even if it is coming from your waveguides, right? We had said that the waveguide there generates the electric field as well as the magnetic field, right? And those two will be at right angle and equal with each other. Then you have those high oscillations. And by the time now the signal moves from a transmission line, whether a waveguide or some conducting material into an antenna, these charges will have accelerated, and as they're accelerating, then electromagnetic waves will be generated. And this is what will be basically produced. And take note, with constant DC current and voltage, you actually get zero radiation. The next important aspect in antenna is how do you design antennas? There are certain requirements in an antenna as you are designing. The first requirement is that you must determine at what frequency you want this antenna to operate. Remember, if the frequency is zero, there will be no radiation. So the antenna must be operated at a certain frequency. And in your design, you must ascertain this antenna that I'm making, at what frequency do I want it to operate? The second thing is gain requirement. Antenna gain in decibels, right? You need to know this. You must calculate this. If I know the directivity, I know the efficiency that I want to achieve here, I can ascertain the value of antenna gain. Then the radiation pattern. Are you going to radiate this electric field, right? Are you going to radiate, in which direction are you going to radiate, right? Is it going to be omnidirection or is going to be directional? Is it directional meaning at a certain angle? Omnidirection, it means you are radiating at 360 degrees, basically all around you. Then you must also know the size, right? For dipoles, we talked of the length, but you must also know the dimensions in terms of the antenna aperture, right? For the receiving antennas. because it is the diameter of that aperture that will determine how much that antenna will receive some signals. So you find that if you have a smaller dish compared to a bigger dish will likely capture more signal and concentrate them at the low noise block than a one that has a smaller aperture. So size in terms of aperture, size in terms of length, if it's dipoles, also matters. Then the last designing requirements is efficiency. Remember, efficiency contributes to gain. It's related to gain. The lower the efficiency, the lower will be the gain. And if the gain is low, that means that antenna will not radiate a lot of signals. So with these requirements, then we need to know now the design steps. So first of all, select the antenna type as the first step in designing your antenna. So what type? If it is parabolic, okay, I'm going to have a parabolic antenna. I'm going to have a Yagi wood antenna. I'm going to have a dipole here. So you select the type, right? Calculate dimensions based on wavelength. So based on wavelength, you can calculate dimensions of the aperture or the dimension of the length. Again, after that, choose the substrate material. This is very common, especially for the patch antennas. Choose the substrate or material to be used. And then you may want to simulate this first before you actually fabricate a prototype. It's in fact in a design, you first simulate. That's why you need to have to know some of the simulating software such as HFSS, CSS, CST, and many others, that can be used to simulate. So you simulate and you have see the design, on a computer. And then now, because in the simulation you will have known how the gain, how it is performing, what sort of dimensions will have been known. Now, by the time you finish these simulations, you are ready to fabricate or basically make the actual prototype. Make the actual prototype. We call it prototype at this stage because once you have made that prototype will need to be tested further to see whether it is behaving as per simulations. If you find that it's actually behaving as per simulation or even better, then that's when now you can do what is known as, now that's a stage where you are doing testing and optimization. So once you are satisfied with all the tests and all the you've done all the things that needs to be corrected, that's optimization. Maybe you needed finally prototype, maybe needed to have more dimensions, more or less dimension. So you are optimizing for maximum gain, for maximum performance. So once you're satisfied with your test, that's when now you order for mass production. By the way, these design steps are common in almost in the making of most of the engineering products. You follow through these types of similar steps. So you simulate, fabricate a prototype, test it. If you are satisfied, that's when you produce them in mass. Okay, otherwise, the last part of this lecture is to talk about where would you apply these antennas. You can apply them in many systems that are wireless, such as satellite communication system, mobile communication systems, 4G, 5G, Wi-Fi systems, uh, WiMAX systems, radar systems, Internet of Things devices that communicates wirelessly. So in general, all wireless communication systems needs an antenna. Whenever you see a Wi-Fi, just know that there is an antenna there to transmit a signal to your phone, or even your very mobile phone. It's actually transmitting a signal to a Wi-Fi using an antenna. Your own laptop is transmitting a signal from your laptop to either the Wi-Fi device or from your laptop to another mobile phone. So there is a lot of use of antennas in almost all wireless communication systems. In fact, every wireless communication system means that either it is receiving electromagnetic waves, which is then converted into an electrical, that is if it is working as a receiver, And if it is working as a transmitter, it means it's converting electrical energy into electromagnetic waves, and then these are broadcasted in a certain direction via antennas. Antennas are widely used, or virtually all wireless communication systems, and they are very, very important also in microwave engineering. Remember, in microwave engineering, you're operating in frequencies above 1 gigahertz. So Wi-Fi system already, the frequency is the 2.4, 2.6 gigahertz. Radar system is also the frequency in the gigahertz. Satellite communication. Now we have 5G also going into 5G, 6G mobile communication system. They are all operating in the gigahertz. So you need antennas. But antennas can also be used below the microwave frequencies. You can use them in television, radio. Those frequencies are essentially below microwave range, but you still need antennas. Otherwise, with this, I'll end this lecture. I've given some tutorials for you to practice. There's question 1, there's question 2 for you there, and question 3, which I would want you to attempt as a tutorial. Thank you. This marks the end of our lecture.